So the t-test document starts with a list of some of these statistical symbols and equations, and you'll see most of these again, but for example, the uppercase N we probably won't use at all because this is representative of total number of individuals in a population, and we are usually looking at a sample of individuals in a population, small n. You saw small n when you were calculating your confidence intervals. That's the same number. Degrees of freedom I'll talk about in just a minute. X sub I is a single measurement because I basically means an individual measurement. S is standard deviation. You've seen that symbol already. And if you square it, we get a number called variance, and we will use that in the t-test calculations. SE stands for sample standard error. We will also use that in the t-test calculations. And you've already got a little bit of practice with confidence intervals, and we'll come back to this equation for the t-test as well. Coming back briefly to this symbol right here, DF, it stands for degrees of freedom. And this is a concept that is pretty commonly thought of as a confusing concept in statistics. So Dr. Strode has a pretty nice way of describing what degrees of freedom means, and I'm going to have him do that for us now.
So I'm going to talk about sample size and degrees of freedom. Now let's pretend that you have a field and you're interested in knowing something about the population of grasshoppers in that field. But you don't have the time or the resources to measure every single grasshopper. So you're going to take a sample. Let's say we choose that our sample size is going to be 10 grasshoppers. And so we use the symbol N for sample size, and so my sample size, I've decided, is going to be 10. Now before I measure anything about these grasshoppers, every single of my 10 measurements is free to vary around some physiological range. So let's say that I want to measure the length of their jumping legs, their back legs. I want to measure this length. And so there's going to be some shortest leg out there and some longest leg. So there's a range. And before I take any measurements, I have 10 degrees of freedom. So I'm going to make 10 measurements. All 10 of them are free to vary around some minimum and maximum. So before I take any measurements, my sample size is equal to my degrees of freedom. All right, so let's say I'm going to go out and I'm going to do the measurements. I collect 10 grasshoppers, and I make 10 measurements. And so my measurements are going to be in millimeters, and this is going to be, we'll call this leg length in millimeters. And here will be my measurements. And let's say that my measurements are, I'm just going to make up some numbers, 33, 24, 18, 14, 32, 21, 35, 29, 28, and 27 millimeters. Those are my 10 measurements. Now, the first thing I can do with these 10 measurements to infer something about the population is to find the mean. So I'm going to calculate the mean, and the symbol, as you know, for mean is this X with a bar. So I calculated a mean of 26 millimeters. So the average or mean leg length for my sample of my 10 grasshoppers is 26 millimeters. Now, I know something about that sample. I know that the mean of this sample is 26 millimeters. Now let's say that I take all of these grasshoppers and I put them back in a bag, and I shake up the bag. And I start pulling them out and measuring them over again. Now, when I pull that first grasshopper out, the measurement of its leg is one of these 10. So it's free to vary among any one of these 10. So let's say that first grasshopper I pull out is number 3. And I measure it and I set that grasshopper aside. And I'm going to pull the next grasshopper out. that next grasshopper's leg length is free to vary among the remaining 9. I've already got one measurement. It's free to vary among the remaining 9, and it's this one. And I continue to pull grasshoppers out and measure them. And I get all of these measurements, and I've got 2 grasshoppers left in the bag. Now that second to last grasshopper I pull out, its leg length is free to vary among the remaining 2 grasshoppers. And it turns out it's this one. There's 1 grasshopper left in the bag. Is its leg length free to vary? It's not. I already know the mean. The mean has to come out at 26 millimeters. So that last grasshopper is known and not free to vary. So once I calculate a mean, the degrees of freedom for this set of data equals my sample size, n, minus 1, which in this case equals 9.
The t-test is an example of something that we call inferential statistics. And inferential statistics basically means that instead of being able to study an entire population, we only have access to studying samples of that population, and therefore we have to infer information about the entire population by studying the sample. So you'll see that all of the statistical tests that we learn about in our class will be an example of inferential statistics. Now, there's a very common idea in all of these statistical tests that we are going to be learning about this year. And if you don't grasp this idea, then it's pretty hard to understand the overall interpretation of statistical results. So there's something that's called a statistical null hypothesis. And this is very different from an experimental hypothesis. So I'm going to let Dr. Strode do a little explanation about what a statistical hypothesis is.
So let's say we go back in the field and we realize, oh my gosh, there isn't 1 species of grasshopper, there are actually 2. And we label them A and B, and we wonder, is the leg length of the A species different from the leg length of the B species? So we do the same measurements on 10 grasshoppers of the B species. And here are those 10 leg length measurements, and we get a mean of 17. Now obviously, 17 is different from 26. So we can observe that this mean is different from this mean. But is it possible that because of our sampling, we got this difference between these 2 means by accident, and they really aren't different? Is that possible? Sure, it's possible. And so it could be that the means are actually the same, and if we did more sampling, we'd find out that, well, gosh, they're not different at all. And so when we do inferential statistics, and all of these inferential statistical tests that you're going to learn, we are testing something called the null statistical hypothesis. Null statistical hypothesis. And the symbol we use is H for hypothesis, sub 0 for null. So in this case, we observe that the means are different, 26 and 17, but we could have gotten this difference by accident, and it really is the case that the means are the same. So our null statistical hypothesis is that the mean leg length for species A is actually the same as the mean leg length for species B, and we got these differences in our sampling by accident. The alternative to that, called either H sub A, or you might also see it as H sub 1, this is the alternative hypothesis, is that the means are actually different and therefore not equal to each other. And so when we do statistical hypothesis testing, we are testing the probability that this is true.
Another concept that you see whenever we do statistics is called the alpha level. And so the alpha level can be pretty confusing, and I'm going to have Dr. Strode do a quick explanation as to what that entails.
Back to these two means, we do observe, indeed, that they are different. This is 26, and this is 17. And we must wonder, did we get these differences by accident? What is the probability that these two species are actually the same and we just got these means by accident? Is the probability, symbolized by p, is it 0.5? If the probability of getting this difference by accident is 50-50 or 0.5 or 50%, are we comfortable concluding that they are in fact different? I'm not comfortable concluding that these two are different if the probability that they're not different and that I got this by accident is 50-50. What about if the probability is, whoops, I meant to put a 5 there, is 1 in 4. Am I comfortable with that? I'm not comfortable with that. What about a 1 in 20 chance, or a probability of 5%, or a probability of 0.05? Am I comfortable with that? Actually, I am. I'm comfortable concluding that these two means are different if the probability that I got them by accident is 0.05. We call this level of probability. We call this alpha. And we set this probability at 0.05. So this is the level at which, the level of probability at which I am comfortable concluding that these two means are indeed different and did not occur by accident.